This is a May-June 2023 variant 42 question. Number 9A carries 2 marks. You have to define mass defects. Mass defect is defined as the difference between the mass of the nucleus and the total mass of the nucleons when the nucleons are infinitely separated. Then for part B, table 9.1, which is this table here, shows the mass defect of 3 nuclei. This is your deuterium, this one is a tritium, and this one is a helium. The nuclear fusion process in a particular style is described as this equation. This is the equation that describes the nuclear fusion reaction, where X is a particle, there's no mass defect. Part 1, you have to state the name for particle X, and part 2, show that the energy released when one nucleus helium is formed in this fusion reaction is 2.8 times 10 minus 12 joule. When you do this question here, you need to know 2 things. Number 1, you need to know that the proton number and the nucleon number are conserved. This means that the total proton number on the left-hand side must be equal to the total proton number on the right-hand side. The total proton number for deuterium and tritium is 1 plus 1 equals to 2. And then the total proton number for helium is also 2. Therefore, your X has a proton number of 0. Similarly, the total nucleon number for deuterium and tritium is 2 plus 3, which is equal to 5. So the total nucleon number on the right side must also be 5. Since the helium has a nucleon number of 4, that means your X must have a nucleon number of 1. So the nucleon number for X is 1, the proton number for X is 0. So that is a neutron. So therefore, your X is a neutron. The second thing you need to know is that the total mass of deuterium and tritium, which is M1 gram or kilogram, is larger than the total mass of helium and neutron, M2 gram or kilogram. So M1 minus M2 is the mass defect, delta M, and is converted to energy by using the equation delta E equals to delta M, mass defect times C squared. So now we can do your part 2. You can get the delta E, delta M from the mass defect, which is equals to 0.030377 minus the sum of 0.002388 and plus your 0.009105. This will give you 0.01884 atomic mass unit. So that you can find delta M. Delta you can find energy released by using mc squared. But before you can use delta E equals mc squared, you must convert your mass in atomic mass unit to kilogram. We know that 1 atomic mass unit is equal to 1.66 times 10 minus 27 kilogram. Therefore, 0.01884 atomic mass unit times your 1.66 times 10 minus 27 will change your atomic mass unit to kilogram. Then you multiply with C squared, that will give you 2.8 times 10 minus 12 joule. In part C, the star in B has a radius of 2.3 times 10 power 9 meter and a luminosity of 1.4 times 10 power 28 watts. All the energy released from the formation of helium is radiated away from the star, and all the energy that's radiated from the star has been released in the formation of helium. We know that in this equation, the energy release is 2.8 times 10 minus 12 joule as calculated from the previous page. So we have to calculate the mass of helium produced per unit time by the fusion process. Before we can do this, which carry 3 marks, we must first calculate the total number of helium atoms formed per unit time. And that will be equals to 1.4 times 10 power 28, which is the luminosity divided by the energy released when 1 helium is formed. That will be 2.8 times 10 minus 12. This will give you 5.0 times 10 power 39 per second. That means this number of helium nucleus is produced in every 1 second. Next, you must find the mass of 1 helium atom. We take 4 because the nucleon number in helium is 4. and the mass of one nucleon is equals 1.66 times 10 minus 27 kg. So it means the mass of one helium atom is 6.64 times 10 minus 27 kg. Then after that, we can calculate the total mass of helium produced per unit time. 6.64 times 10 minus 27 is a mass of one helium times the number of helium atom produced in 1 second. This will give you 3.3 times 10 power 13 kilogram per second. Then in part 2, to calculate the surface temperature of the star, we use Stefan-Boltzmann equation. L equals to 4 pi. Stefan-Boltzmann constant is a constant proportionality, R square and T4. We know that the luminosity is 1.4 times 10 power 28. We know that your Stefan-Boltzmann constant or the constant of proportionality is 5.67 times 10 minus 8. And we know the radius of the star is 2.3 times 10 power 9. So you can find the temperature, and the temperature is found to be 7,800 Kelvin. When you do this question, you must remember that one atomic mass unit is 1.66 times 10 minus 27 kg. The speed of electromagnetic wave is 3 times 10 power 8 meter per second. And the mass of one helium is equal to 4U, is 4 times 1.66 times 10 minus 27 kg. And your Stefan-Boltzmann constant or the constant of proportionality is 5.67 times 10 minus 8 watts per meter square per Kelvin to power minus 4, per Kelvin to power 4. This is a summary of the facts that you must know to solve this question. Number 1, you must be able to define mass defect. Number 2, you must understand that nucleon number and proton number are conserved in nuclear processes. Number 3, you must be able to calculate the mass defects of a nuclear fusion reaction and use E equals to mc squared to calculate the energy release. And finally, you must use Stefan-Boltzmann law, luminosity and radius r to calculate the surface temperature of a star by using Stefan-Boltzmann equation, which is L equals to 4 pi constant proportionality R squared to power T4.